Hello, and welcome to Integration by Substitution Part 2. My name is Tuesday J. Johnson. I'm a lecturer at the University of Texas, El Paso, and an assistant professor at Doña Ana Community College. Chapter 4, Integration, comes to us from Larson's 11th edition calculus text. Section 4.5 is Integration by Substitution, and I divided it up into 2 lectures. This is Part 2, where we're talking about definite integrals. So, we're going to review the definition of integration by substitution in general. And this definition, and feel free to pause if you want to read through it, but we have a product rule for derivatives, we have a quotient rule for derivatives. We do not have a product rule for integrals, we do not have a quotient rule for integrals. We have a chain rule for derivatives. The good news is, integration by substitution is the opposite of that chain rule for integrals. Right? So it undoes a chain rule. If you need to, review composition of functions, the chain rule, and if you want to use my terminology, I encourage you to listen to my lecture on composition of functions. That should be 1508, somewhere around section 1.8, I think. Algebra of functions. Composition is its own special lecture. It's a part in that section. So, inside and outside functions related to composition. So, let's evaluate the definite integral using substitution. The integral from -2 to 4 of x squared times x cubed plus 8, the quantity squared, dx. When using the method of substitution with definite integrals, right, if we're going to change this x into an integral involving u, we're also going to change the limits of integration. Do the change up front, and we never have to go back at the end. So, my inside, x cubed plus 8, is going to be my u. The derivative is 3x squared dx, but I don't have an extra 3 hanging out anywhere in my integrand, so I'm going to divide both sides by 3 to get 1/3 du equals x squared dx. But also, when x is -2, I can substitute x as a -2 and find my u value. My new u value will be 0. -2 cubed plus 8, that's a -8 plus 8 is 0. When x equals 4, my upper limit of integration, u is 4 cubed plus 8, which is 64 plus 8, which is 72. So what I'm going to do is these limits of integration are in terms of x. So when I switch my integral to terms of u, I'm also going to change my limits of integration, so they're also in terms of u. X cubed plus 8 all squared becomes u squared. X squared dx, that's going to be replaced by 1/3 du, 1/3 du. The 1/3 is out in front. The integral of u squared is u cubed over 3. I'm going to evaluate from 0 to 72. Yeah, kind of quick and dirty, but I'll learn better typing techniques here in a little bit. This is 1/9. 72 to the third minus 0 to the third. 72 to the third divided by 9, that's a 41,472. That's a pretty huge area. But, I'm finding the antiderivative from 0 to 72, so I guess that makes sense. Alright, so when you change to u for your integrand, make sure you change to u for your limits of integration as well. The integral from 0 to 1 of x times the square root of 1 minus x squared dx. If u is 1 minus x squared, then the derivative is minus 2x dx. I don't see an extra minus 2 hanging out here, so I'm going to divide both sides by a -2, and I'll have -1/2 du equals x dx. When x is 0, my lower limit of integration, u equals 1 minus 0, or 1. When x equals 1, my upper limit of integration, u equals 1 minus 1 squared, which is 0. So keep in mind, when x is 0, my u value is 1. Whereas, when x is 1, my u value is 0. So I have to put them in the correct spaces. Not spaces, but the correct locations. I'm replacing x equals 0 with a u equals 1. So where the x equals 0 was, I put a 1. I don't naturally just put them in order from lowest to greatest. I put them in the correct order based on their substitutions. So, the integral from 0 to 1 of x square root of 1 minus x squared dx is, all right, the x dx is replaced by a negative 1/2 du. The limits of integration, 0 to 1 on x, are replaced by 1 to 0 on u. The square root of u, so that's u to the 1/2 du. The negative 1/2 out in front, and the u to the 3/2 divided by 3/2, which becomes 2/3. And you're thinking to yourself, hey, Tuesday, where's the negative? Here's what I did. The negative that was here, and the negative in switching the order of my integrals. All right, I switched the order on the limits of integration, and I can do that by offsetting the solution with a negative sign. So two negatives make a positive. And that's why this one is positive. I used this negative, and I got a negative in switching my order. It's the order of subtraction, so it's just going to be off by a minus sign. 1/2 times 2/3 is 1/3. U to the 3/2 evaluated at 1 and at 0. 1 to the 3/2 is 1, 0 to the 3/2 is 0. 1 times 1/3 is indeed 1/3. Example number 3. The integral from 0 to 2 of x over the square root of 1 plus 2x squared dx. Inside a denominator, inside a radical, inside I'm going to let u be 1 plus 2x squared. The derivative of this, 1 plus 2x squared, is a 4x dx. I don't have an extra 4 hanging out, so I'm going to divide both sides by 4 and get 1/4 du equals x dx. So my x and my dx are taken care of. The square root of, I've taken care of the 1 plus 2x squared. Now I need to handle my limits. When x equals 0, u value is 1. When x is 2, 2 squared is 4, 4 times 2 is 8, 8 plus 1, u equals 9. So the integral from 0 to 2 of x over the square root of the quantity 1 plus 2x squared dx is 1/4 the integral from 1 to 9 of u to the negative 1/2, because it came from the denominator, du. The 1/4 is hanging out. The integral of u to the negative 1/2 is u to the positive 1/2 divided by 1/2, but instead of dividing by a half, I'm going to multiply by 2 over 1. Evaluated from 1 to 9. I'm going to clean this up a little bit. 2/4 is 1/2. U to the 1/2, that's the square root of u. And notice how nice this is. I'm evaluating from 1 to 9. So that's 1/2 times the square root of 9 minus the square root of 1. The square root of 9 is 3. And the square root of 1 is 1. 3 minus 1 is 2. Half of 2 is 1. That is our definite integral area under this curve between these x values above the x-axis. A little fact, and we've used this a couple of times, but we haven't really seen the fact before. If you have what I call a symmetric interval, and a symmetric interval in my world, and I think I just made that up today, I don't know, I've never called it that before. It's an interval where 0 is the midpoint. Think of it as where the fulcrum goes in order to balance a plank. So if f is an even function, then the integral from negative a to a of f of x dx is double the integral from 0 to a of f of x dx. Whereas, if f is an odd function, and we've seen several of these, then the integral from negative a to a of f of x dx is 0. Remember, this is area. So if we take a basic odd function, my favorite odd function, drawn poorly, is y equals x cubed. And if I go from 1, actually I'm going from negative 1 to 1, what this is saying is the area under the curve is exactly equal to the area above the curve, and that's why the area turns into 0. They cancel each other out. This is called a negative area. And I know areas can't be negative, but the negative refers to below the axis. A positive area refers to above the axis when we're looking at graphing. So a couple of facts that might make some of your integrals easier. That's it for integration by substitution with definite integrals. Thanks for listening.